Hey guys, this is Manuel with episode 2 of our particle course. Let's continue the journey into the land of particles. As you can see, I have the same object here in the viewport already loaded in, like in episode 1, but today I want to pull off a very different effect. Today I want to make the particles conform to the surface. So we want to emit some particles on the surface and then introduce a constraint such that they don't leave the surface, but instead move along the surface of this object. That is very handy and looks beautiful. And it's a handy technique for a lot of different effects. So let's get started. The very first thing we need is a normal SOP. Because we need the normals later on. That is why I create them here and set them to points. Let's quickly check if we have them, and here they are. And now let's quickly pull off the same trick as last time. So lay down a null, connect the normal to the null and call the null out obj. And now go one level up, create a new geonode, call it obj. And inside let's lay down an object merge and point it to this null out obj. And that is just for having the object and the particles visible at the same time. Because now we can append a scatter SOP, like so, creating particles. And now that we have this separate object, we see the object underneath. We need a lot of particles this time, so let's scatter 50,000 points, covering the entire object in particles, like so. But before we send these particles to Popland, let's first displace them a little, because at the moment they are exactly on the surface. Instead, I like to have a shell of particles, so a certain thickness around the object covered with particles. That can easily be done with a VOP, so lay down a point VOP. Connect it here, call it displace, and dive inside after making it visible. There is a node inside of VOPs that is called displace along normal, and that is exactly what we want to do. We want to take the points, or the position of the points, and displace it along the normals. But how far? Well, if we just connect P to P, and then connect the displaced P to P, we can create a displacement amount, and you see the points are moved along the normals. But we want to do this randomly. So lay down a random node, and we want to give every point a different random value. So we need a different seed for each individual point. And we could use ptnum, because ptnum is different for every point. Now we can connect this random output here to the amount, and you see we get this because now each point gets a different amount value between 0 and 1, but that is too large. So lay down a fit range and put it here between the random and the displace, like so. And let's transform our range 0 to 1 to something smaller, like 0 to 0.05, say. And now you see I have a random displacement on my points, giving me a shell of particles that has a thickness of 0.05. That is exactly what I want. It looks nicer later on. So now I have displaced points, and let's care about the attributes now. The first thing I want to set is some initial velocity. This time I use a VOP for this because I want to use noise, and working with noise is easier inside of VOPs if you ask me. So lay down another point VOP, and connect it at the bottom and call it set initial velocity, and dive inside. And inside, not much happens. It's just an anti-alias noise that I connect to the P port here. Sorry, P to pause, like so. And then I want to be able to adjust it a little. So let's append a multiply and promote this second parameter, like so. And now let's set this to V. Now we have velocity. Very important though is that we set the signature of the anti-alias noise to 3D input 3D noise. That means it outputs a random vector instead of a random float. And as velocity is a vector, we need vectors to set velocity. Now we have random vectors for velocity. But at the moment the velocity vectors are all 0 because, remember, we are multiplying them by this input here. And it is set to 0 by default. So let's set this to 1 for now. And if you turn on show velocity, you see all the random velocities that you get here. Like so. Great. So the last attribute we want to set is, as last time, p-scale. This time using a wrangle, because it's the quickest way to just set p-scale to a constant value. And just write at p-scale should be 0.005, say, for now. And call the wrangle set p-scale, like so. Now we are prepared. We have points with velocity, and we have p-scale on our particles. Time to create a popnet. So lay down a pop network and connect our prepared points to the first input. Make the popnet visible and dive inside. Inside you find all the familiar nodes, and the blue points tell you that the points are coming in. But the source is set to scatter on surfaces by default, and we want to switch this to all points because points are coming in. Now we get particles. We can turn off the guide. If you ask me, this is just distracting. And here you have the points. If I press play now, I get a lot of particles, because it's generating particles in each and every frame. And with this simulation, I don't want that. I only want to create the points on frame 1. And after that, I don't want to create more points. So to do this, let's switch to the Burst tab. Here you find impulse activation, and it is set to 1. And this parameter controls if points are created or not. So if this is set to 1, points are created. Let's quickly set this to 0, and you see no particles. So to only generate particles on frame 1, we can put an expression here. So write $f, which is the current frame, is smaller than 2. This expression evaluates to 1 if we are on frame 1, but if we are on another frame, this evaluates to 0, turning particle generation off. That's exactly what we want. If we now press play, you see we get an initial set of particles on frame 1, and after that, no more particles are generated. And they are flying off in random directions because of the initial velocity we set. But now let's make this a little more interesting by introducing a pop wind. So lay down a pop wind. And we can wire the pop wind here between the source, and the wire pops into here. But now comes the specialty of DOP networks. DOP networks work a little different than SOP networks. The execution order is not only top-down, but it is top-down and left to right. And that means if I don't connect this pop wind here, but instead wire it into this merge to the right, I get exactly the same effect. It's a little strange, but this pop wind acts on all the particles, so all the particles that are stored inside of this pop object, without an input. So that means first comes the source first input, because it is the leftmost node, and after that, pop wind is executed. So today let's do it like this, just to get used to it, because you see this a lot in DOPs, and it is exactly the same. So putting it between source and this merge is the same as putting it as a second input to the merge. So now I have this pop wind here, and if we press play, I don't get any difference because I have an amplitude of 0, let's say 0.15. And now I have some chaotic behavior. Very nice, but too fast. So as last time, let's quickly create a pop drag, and this time connect it like this. So now the execution order is the same as if putting the pop drag beneath the pop wind. First comes the source, then the pop wind, then the pop drag, left to right. Now my particles are flying in all directions, but they are not sticking to the surface. So how do we make them stick to the surface? Well, we want to alter the velocity. Okay, here is our surface. Here is our particle, and it has a velocity vector that points in any direction. We set this initial velocity that is driven by noise, and then the force, the wind force, is integrated to velocity 2, so the velocity vector is totally random. That is why we see the behavior that we have. And what I want to do now is I want to keep this velocity, the length of the vector, but I want to change the direction. I want to change the direction of the velocity such that it is tangential to the surface, because I want the particle to move along the surface. How can I transform this velocity vector into a vector that has the same magnitude but is parallel to the surface? Well, there is a little trick, and this trick uses the normals of the surface. Remember, this surface has a normal pointing in this direction. And what I can do now is a double cross product to sort of rotate this vector. Remember, a cross product takes in two vectors, like so, and then it generates a third vector that is perpendicular to both of them. So it generates a vector that is perpendicular to the plane spanned by these two vectors. So here you get a right angle. That is what a cross product gives us. So what we could do in our case is we could just take the normal of the surface at the spot where the particle is, and then we can create a cross product between the velocity vector and this normal. So that would be the plane spanned by these two vectors, and this here would be the result of this cross product. Now we have a vector that is perpendicular to both of these vectors. But that is not enough, because we want to keep velocity, but just move it in this direction here. So what if we just create a second cross product, this time between this generated vector and the normal? That means we are creating a vector that is perpendicular to this plane here, and this vector has exactly the direction that we are after. So this vector will be in the direction of the velocity, sort of, but tangential to the surface. So by just creating two cross products in a row, we can transform this vector. The speed will be the same because the magnitude is preserved, and the overall direction will be the same too, because we do this double cross product. So let's implement this inside of Houdini. I want to implement this using a pop-wop. So create a pop-wop. But before we connect it, let's think about where to put it. Now it's time to think about these two inputs on the pop solver. If you hover over the inputs, you see that this third input is called post-solve. And the second input is purple too, but it is called pre-solve. So that means nodes connected to the third input are executed after the pop solver does its work. So the pop solver calculates the position of the particles from the velocity and the velocity from the forces. And after that, all of this is executed. And everything that is connected to this second input is executed before this calculation happens. So instead of connecting our pop-wop here at the third input, we want to connect it at the second input, because we want to modify the velocity before the pop solver uses it for its calculations. So connect this pop-wop to the pre-solve input and call it stick to surface. And let's dive inside. To be able to calculate our cross product, we need two vectors, the velocity that comes out of this v-port, and then the normal of the surface near to the particle. But I'm not interested in the point of the surface. Instead, I'm looking for the parametric location on the surface. So I want to find the exact location on the surface where the particle is nearby. And I can calculate this location by using XYZ dist. This node expects an input geometry and a position. So connect P to the position, and it will look for the parametric location on the closest primitive. So out comes a primitive number and then a prim_uv vector that is the location inside of this primitive. For this node to work, we have to connect the input. And the input is the surface where the particles are on. How can we access this surface? Well, if you look one level up to the pop warp and go to inputs, you see you can set the inputs of this pop warp. The 4 inputs, 1, 2, 3, 4, are not defined at the moment, but you can define them. So go to this drop-down for input 2 and set it to second context geometry. Second context geometry refers to the inputs of the popnet itself. So let's take the surface that we are interested in and let's wire it to the second port of the popnet, like so. So the normal here goes directly into the second port. And now this information is passed on to the pop warp because we set it here. And I just use input 2 because it makes more sense to me if I have it coming in over input 2 into the popnet. I want to have it on input 2 inside of the pop warp. Now that we said that, this information is coming out of this port. And I can connect this to the XYZ dist. As I told you, the XYZ dist is not returning a position, but it is giving me a primitive number and a prim_uv vector. So I need a second node to read the actual position. And this node is called primitive attribute. So lay down a primitive attribute node, prim_uv. This node expects the same geometry information, and then a primitive number, and a UV vector. And now it reads any attribute from exactly this location on the surface. So let's specify that we want to read n here. So now this A_data puts out a vector, the normal, that is living on the closest location near to our particle. That is exactly what we want. Now that we have this information, we can lay down a cross product. And we can do a cross product between the velocity connected to the second input and this normal connected to the first input. And now, as we planned, let's create a second cross product. And let's connect the normal to the second input and the outcome of the first cross product to the first input. So now I'm doing this double cross product. And the result of this just goes to velocity. So, if everything went right, we now have a constraint that alters the velocity before the pop solver uses it. And this should make the particles stick to the surface. Let's test this. And now look at this. The velocities are still pointing in the principal direction as before, but now the constraint makes the particles move along the surface because the velocities are bent. But because we don't project the particles onto the surface, they will deviate from the surface over time. It's only that the velocities are bent to be tangential to the surface, so the particles will move away from the surface more and more over time. And we want to use this to our advantage, because as soon as the particles are a certain distance from the surface, we want to let them loose. We want to have them fly off into midair. How can we do that? Well, first we can group them. So lay down a pop group. And this allows you to group particles as you would group points in SOPLAND and connect it here after the pop drag. And turn on expressions and you have in group 1 here, and the group name could be off, for example. So now every particle is set to the group off. And we can visualize this by using a pop color connected here after this pop group and constrain it to only work on the off particles. And you see everything turns purple because all the particles are set into the off group. But instead of just creating a group for all the particles, we want to use a logic, and we want to use the distance from the particles to the surface. But how can we access this information? Well, we are calculating this distance here inside of this network because it comes out as a byproduct from this XYZ dist node. Here we have this distance port, and that is just the distance to the parametric location that is closest to the particle. So why not binding this with bind export to an attribute? Let's call it myDist, like so. So whenever this calculation takes place, the distance is stored to an attribute. Now I can go to the pop group and write an expression here. And this expression should be an if statement. So write if the attribute myDist is smaller than 0.1, say, and then brackets. In this case, it should go into the group off, like so. Let's press play, and you see that the color is not changing, and that is because we have to add one more thing. At the moment, the color is set, as all the particles are first in the off group, and then the color just sticks to the particles. So we have to create a second pop color and set it to something else, say to a green, and put it here to this merge, but in front of all of this. So go to the merge and click this little arrow to move the pop color before this pop group and pop color. So that means that all the particles are colored green, and then the ones that are in the group are colored purple by this node that is constrained to work on the group only. So now it works, the particles start purple and then they turn green the further they are from the surface. So now we have one last thing to do, and that is to tell the stick to surface to only work on the particles that are inside of the group. So just go here to the stick to surface and set its group constraint to off. And now let's see what that gives. And you see, as soon as the particles turn green, they leave the surface, because they are no longer in the off group, and that means that the stick to surface constraint does not act on them anymore. And now you have the effect that you saw in the beginning of this video, where you have a lot of particles moving along the surface of the object, and then the ones that try to escape really can escape. So let's go one level up and press play with the object in place, and you see that is this nice effect. I hope you learned a lot in this tutorial, and stay tuned for more particle stuff to come. Thanks a lot for listening. See you next time.